Yeah.
I'm still kind of getting set up. Let me just, all right. Okay, go ahead. I want to catch this first question. All right. And then, all right. So the rock goes up, comes down, and if I heard you right, you said it lands lower than it starts. So the distance traveled would be a negative number. Okay, yeah, totally agree.
So we have solutions that's next to the homework, and I tried to do it without the solution first. And what I did is I made the value of the height negative and then plugged that in, and then I got an answer and it was wrong. And then I looked at the solution, and the solution made the variable negative, right? Like in the solution, it says the equation is h equals vt times at squared, and then the h is negative because the final distance or the final height is lower. And then I tried it that way, and I got a different answer, which was right. And I was just wondering, I obviously did some algebra wrong, right? Because if you made the value negative, that wouldn't necessarily change the answer, correct? Like the value versus the variable negative.
Yeah, let me share my screen, because I think I'm understanding your question, but I think it would be easier if I kind of showed you what I think you're saying in equation form.
Okay.
Let me just connect my phone here. I use my phone for my video camera. And maybe I should even ask you, is this directly on the homework one? Because I can look up the problem.
Yeah, it's on the homework one.
All right, I'm going to look that up too here.
Okay.
Let me just click. Let's see, I got my share screen working, I think. But I'm going to go to your assignments. Okay.
Yeah, it was on homework, because there's one called quiz and then one called reading quiz, and it was on the one labeled homework.
So it says homework, one-dimensional motion?
Yeah.
Okay. So that's loading.
And I think it was problems 7 and 8, I believe.
7 and 8. Okay, so 7 and 8 says free fall with initial velocity, person on edge of a cliff, height h. Yeah, okay.
Yeah. Does it show you, can you see like the solution on the side?
I do.
Yeah, so I first tried it without looking at that, and I used just the regular equation without any negatives added in the equation, but I made the value of h negative when I plugged it in, and then I got an answer, and then it said I was wrong. So then I redid the homework, and it gave me new numbers, and then I used the solution. I just used the equation that was derived in the solution with the negatives. And then I plugged in positive values, and then it said I was right. So yeah, just wondering. I probably did algebra wrong or something wrong, because I think it doesn't matter, right? If you choose the value to be negative and then you plug it in, or you make the variable negative. You know what I mean?
Yeah, that's why. So let me just run through, because what I'm hearing you say sounds good, and I can't figure out why you got a wrong answer. And so I guess I too would be leaning to what you said, that maybe you did an algebraic mistake here.
Yeah, but and I have my scratch work in front of me, just so I can follow along. See me.
Okay. So if I was doing this problem, I guess I would start with here. Let's see. Well, let me go back up and read it here. It says, a person on the edge of the cliff of H throws a rock straight up with initial velocity of v naught. At a time t later, the rock hits the bottom of the cliff, moving downward with a speed of v. So if I were to write out what I call equation number 1, v equals to v naught plus at. And maybe I should ask you, does that equation look familiar?
Yeah, it does.
And then the other important one, which sometimes we write the x on the right. I'm going to put it on the left just for now, because that's kind of how you described it to me.
And then you can call that x minus x naught just h, right?
Okay, good. So that's kind of the first thing, is to kind of
Yeah.
The phrase I like to use is kind of read the math, and what does that actually mean? And that means the final position minus the initial. And so, as you said, that would be, and here's where I got to be careful, that would be a magnitude of h, the height of the cliff. But as you said, it would be a negative number in there.
Okay, yeah. So I did that when I got the right answer, but when I got the wrong answer, I didn't put any negatives in H. I just made the value I plugged into H negative.
Yeah, so you say that's why I'm saying that's kind of the same thing. So, all right, so let's say I have this problem here, and I try number I'll try, I guess it's 8. And so what would go in number 8? Oh, and here's something I'm not sure about. When I call mine up, do we get the same numbers, or is there a algorithm in this that gives every student a different number?
I think it's different numbers because I got different numbers when I redid the assignment. Yeah, I do have the original numbers that I used though.
Okay, let me use your original number. What was your H?
22.5.
And then this is for number 8, right?
There's 2 problems for this like scenario, right?
Yeah, let's do 8 first, just because I think that gets to your question better.
Okay, is that asking for what's that asking for?
So that's asking for initial velocity.
Okay, I think here, let me find that real quick.
Or whichever one's easier, I could do.
Okay, I found it. Okay, so the one that's asking for initial velocity.
Yeah.
Okay, yeah, so my H for that problem was 17.4 meters.
Okay, so, and then I'm going to put 17.4 and then put a minus. And if I'm hearing you right, that's what you did.
Yeah, I put H, so like when I started the problem, I put H equals negative 17.4.
Okay, yeah. And so that sounds good so far. And then of course, V naught is what we're looking for. Okay. And then the time is given.
Yeah, I did it said 3.50 or 3.5.
Okay, so 3.50. Okay.
Mm-hmm.
And then, and maybe I should ask you about this. Be real careful here. I'll come back up here. The original equation has the acceleration.
Mm-hmm.
Its value, though, is downward. So did you put in a negative 9.8?
Yes, I labeled, like when I was labeling my known values, I did A equals G equals negative 9.8.
Okay. So you should have an equation that looks like this. Oh, and sorry, I should have put in the time, 3.5 squared. Awesome. Now, let me just try the algebra. I'll grab my calculator here. And so maybe I'll start over here on the left-hand side. That's a negative 17.4. And when I bring this to the other side, that negative becomes a positive, and so it'll be 4.9 times 3.5 squared. Then I would divide by, and maybe I shouldn't do this much math in one step. Let me know if that's too much. What I get, if I've done my algebra right, which is kind of your question, I get a 12.2.
Yes, I definitely did algebra wrong because I actually solved for V naught in variable form first and then plugged in the values. So I must have done something wrong in that step because I got 42 something for the velocity, which was definitely wrong.
Okay.
Yeah, I don't know. I started with the H equals V naught T plus 1/2 AT, and then I substituted in the negative G, so it's H minus 1/2 or H minus 4.9 T squared, and then I just rearranged to solve for V naught. Maybe
Okay.
maybe the H. I think it's the H, but then when I plugged in my value for H, it says I plugged in negative 17.4. I don't know. I think it definitely has something to do with the signs, though.
Yeah. Well, so okay. So I'm gonna try your method, which
Okay.
is to say, why don't we do this in variable form? And so I'm going to put negative h here. And then over here on this side of the equation where I have 1/2 and negative g. Remember now, g is representing a positive number of 9.8 when you do this step.
Yeah. Okay.
All right.
So it would be, so would that, like, so I moved that minus sign and made it like VT minus 1/2 G. Like I just moved the minus sign. And then I think I moved the minus sign and then I plugged in negative 9.8. So it was like a double minus. I think that was
Okay. And that's easy to do and common. So that doesn't surprise me if that's what happened.
So do you think it's smarter to plug in a positive 9.8 and make it negative at first, or just plug in the negative value, you know?
Let me say this. Traditionally, this is the normal way. G is always a positive number.
Okay.
Okay. I know the acceleration is negative. So back here, if you'll notice what I did is I said, here's the general equation. It says plus the acceleration.
Mm-hmm.
So what is the acceleration? The acceleration is a negative g. G is always a positive number in textbooks.
Okay.
And yeah, so
That
never, if you ever see g in a formula, you plug in a positive number. Never plug in a negative.
That makes sense. So it's like the magnitude, basically.
Yeah, right.
Okay. Yeah, that makes sense.
And
so that must be where I messed up, because the double negative would definitely affect the answer.
Yeah.
Okay. Cool. Thank you. That really clears it up.
Oh, good.
Yeah, that was my only question that I had for 120.
That one. All right. Now I'll jump back to Alex here.
Yeah. So from the reading, for third law of forces, it says, although, so it's in describing like the table and the frog, it says, although these two forces are equal in size and act in opposite directions, they're not third law of forces. They both act on the frog. And so I thought I kind of got confused because I thought there were two different like scenarios that were explained for this that seemed to contradict each other. I couldn't find the apple one because I thought there was a description in the same chapter about that.
Okay.
And I thought that was sort of like showing the opposite, that they were like, instead of acting on the same object, they're acting differently. And so it was like saying that's also not their law.
Okay.
So I was just kind of confused about that. Because third law companion forces have to act on different objects. Is that it? Or
yes, give me a second here. Whoops. I'm going to it won't let me miniaturize my Zoom. Maybe I won't miniaturize it. Okay, I'll just move it out of the way for a second here. Let me do a couple things. The first one is I want to call up your textbook. You're talking about this frog. Let's see, this is 102, right? This is the Kirkpatrick book.
Yeah.
And let's see, Newton's laws are explaining motion, right? Is that chapter 3?
Okay. I think so, yeah.
Oh, do you know what page that frog one is?
It was just a part in the reading. It was 52. It
was just part of the reading on page 52.
Yeah.
Because the other thing I wanted to do, I see the frog now. Okay, is to is to say what exactly you're saying is a a common point of confusion, very, very common point of confusion. And that's why your author puts it here. And I want to expand on it, because when we deal with Newton's three laws, the second and third law are closely tied and very confusing. And you could misunderstand them, okay? But you said it right. You said it right that the third law, one of the best ways to work with the third law is to realize that the third law is on different objects, two different objects, not on the same object. So when we're dealing with Newton's second law, we're talking about the forces on that one object. When we're talking about Newton's third law, now there's going to be two objects involved. Okay. And so let me see if I can make sense a little bit better with this table. So here's the table. And it gets even harder because we've got the Earth involved also. So here's the Earth. So we've got a table, we've got an Earth, and I won't even attempt to draw a frog. I'll just say we have a frog. All right. All right. So keep in mind that there's three objects here. And let's focus our attention maybe on the frog, right? And so I say, what forces are on the frog? Because Newton's second law, this is important here, says add up all the forces on that one object. So frog, that would equal to the mass of the frog times the acceleration of the frog. And so everything has to do with the frog. The forces on the frog, the mass of the frog, the acceleration of the frog. That's the second law. Now, the third law, as you're pointing out, is what we call the action and reaction. And so that says that there are two forces, but they're on two separate objects. All right, so watch this for a moment. Let's say we look at the frog and we say, well, what forces are on the frog? Well, it'd be a good time for some colored markers here. Is the first one would be the weight of the frog. The Earth is pulling down on the frog. All right, so I'm going to draw in green a downward force on the frog. I might even label it this way. It is F. Okay, so there's a force. And it is from the Earth. So I'm going to put E for Earth, and it's on the frog. And I'm kind of hoping that notation might help you, because if I think about, say, the third law, I am saying that the Earth is pulling the frog down. Therefore, the frog is pulling the Earth up. And that force is on the Earth. So that's what I mean here by the third law. These are equal and opposite. I'll probably label it this way: force from the frog on the Earth. And so I switch the order of these subscripts, trying to say that these are equal and opposite forces, and they're on different objects. This force is on the frog, this force is on the Earth. So the ones I've drawn in green are an action-reaction pair. Now, let me get a different color. What might stand out here? A red. Okay. So what else is on the frog? Well, the table is making contact with the frog. So I would say then that there is an upward force on the frog from whatever this table is made of. I'll just say the table is made out of wood. So the wood molecules in this table are pushing up on the frog. So I'll put an F for frog. An F for force, but it's from the table, T, and it's on the frog. Now, let me also remember Newton's third law again. There's an action-reaction. So for every force, there's an equal and opposite coming from that object. So remember, this force on the frog came from the table. So right here, where the frog is in contact with the table, there would be a downward force on the table, and I would label it as force on the, well, from the frog on the table. And so these two in red are equal and opposite. And notice they're on different objects. This one's on the frog, but this one's on the table. So the pair in red and the pair in green fall into this category of Newton's third law. They're equal and opposite. But look at the frog for a moment. The frog now has two forces on it. So if I wanted to know the acceleration of the frog, and I would use the second law, I would have to add up all the forces on the frog. And so what would go in this calculation would be just these two forces, this top red one and this top green one. I would not include this red one or this green one because they are not on the frog. I would only include the forces on the frog. Well, watch, I'll keep going with this. You might say, now, wait a minute, doesn't the table weigh something? Yeah. Okay. So this might be enough color difference to stand out, kind of this orange color. But I would say gravity is pulling down on the table. So there would be a force from the earth on the table. And since it's the earth pulling down on the table, then the third law would say there is a force then from the table on the earth. And so these that are in orange would be a third law, an action-reaction. Now, neither one of them are on the frog. So if I'm trying to find out what is happening to the frog, I probably won't even draw these in the diagram. And I'm looking at your author. Your author doesn't even talk about this pair because your author's focus is just on the frog. So why talk about this pair except to talk about it in terms of it might make some clarification for you. You know, it might clarify how the second law and the third law are so closely tied they can get confusing. Now, let me do another one here. Watch this. Let's see if the purple stands out here. The legs of the table are in contact with the earth. So the earth is going to push up on the table. So this would be a force from the earth on the table. Maybe that's a bad notation because I used that notation before. Because the earth I used as gravity. This is a little different than gravity. This is a contact. So let me call it F. That's from the earth, but it's a contact. So I'll go CT. That okay? Contact with the earth instead of gravity.
Sure.
But then, of course, notice that the table is pushing down on the earth. So there's going to be a force that the table puts because of its contact. And again, I drew both of those in this purple because these are action-reaction. They're on different objects. This one's on the table. This one's on the earth.
Okay. So the companion forces have to be exerted by different objects towards each other.
Yeah, so they're equal and opposite.
Okay.
So that's why I guess I've tried to say here, we should have a pair between every set of forces. So between the frog and the earth, that's the green. Between the frog and the table, so that's red. The table and the earth, that's orange. The table and the earth due to contact, and that's purple. And so every gravitational force, so We got two forces of gravity and every contact force. And we got a contact here and a contact here. So I would say there's four forces involved in this problem if you look at all three objects. Now, I must admit, we don't usually want to look at all three objects because it gets pretty complicated. We usually just want to look at all the forces on just one object, like the frog, and then we stop. So I didn't need to do these purple ones or these orange ones if my focus was the frog. I just needed to do enough, and there's two of them that I would add for the frog. But what I am trying to say is I could now apply Newton's second law to either the frog, the table, or the earth. And if I applied it to the frog, there would be two forces on the frog. So I would add up those two forces. If I was trying to find out the acceleration of the table, then right here at the second law, I would do all the forces on the table. And I think there's three of them. There's this red one, which is coming from the frog. There is this orange one, which is coming from the weight of the table. And then there is this purple one, which is coming from the contact with the ground. So if I was doing Newton's second law for the table, in fact, maybe I'll just put it down here. I would have, so for the table, I would have the force from the frog on the table. I would have the force from the earth on the table. And I would have the force of contact on the table. Notice it's all the forces on the table. And then that would have to equal the mass of the table times the acceleration of the table. Whereas up here, if I was doing the frog, Newton's second law, I would add up all the forces on the frog. And the frog has the force from the table on the frog. And it also has the force from the earth on the frog. That would have to equal the mass of the frog times the acceleration of the frog.
Wow.
Okay, so there, and I hesitate to show you all of what's going on because I don't want to overwhelm you, and that's exactly what the author on page 51. He just does these two, and then says, let's add the forces on the frog. He never says, let's add up all the forces on the table. But I don't know, maybe seeing it in its more detailed glory, you'll see that I could actually apply Newton's second law to each of the three objects.
I see. Yeah. Do you know where the apple example was in the chapter?
I don't off the top of my head, but
Yeah, I'm trying to find it.
actually, and just for completeness, I'm going to go Earth. You see, because I could have done this. I could have said add up all the forces on the earth. So there is a force from the frog on the earth. I mean, a frog from the frog on the earth. There is a force from the table on the earth. And there is a force from the contact of the table on the earth. And those three forces together would equal the mass of the earth times the acceleration of the earth. And your author didn't do these steps here. Your author did not bother to look at the motion of the table or the motion of the earth. Your author, knew, and I'm still wondering myself if this was wise on my part to show you all these, because it makes it look really messy. And but at the same time, sometimes when you see the grand picture, you begin to realize, only use the forces on the earth to get the mass of the earth times the acceleration on the earth. Only use the forces on the table and set it equal to the mass of the table and the acceleration of the table. And then when your author is focusing on, it says only the forces on the frog would equal the mass of the frog. So we could actually apply Newton's second law to each of the three objects here. And then likewise, the third law is between every set of forces, and there are four of them. There's two that are contact, the frog and the table and the earth, that's two of them. and the other two are the pole of gravity. So that would be between the earth and the frog and the earth and the table. So there are 4 pairs of Newton's third law.
Wow, that's a lot.
And then there are 3 Newton's second law. Yeah. So again, yeah, we're back to this. That's a lot. Maybe it's too much to try to show you, which is why then your author ignored anything that was not necessary for just figuring out the frog. And so since your author is only focused on the frog, he only applies Newton's second law once. So he doesn't do the table or the earth. And since there's only 2 forces on the frog, he only applies Newton's third law twice, because there's no point in messing with the ones that in my picture are orange or purple, because it's only the green and the red that are on the frog. That's
Right.
what he's trying to say.
So in terms of the vectors, I noticed that the tails are on the object that's exerting the force, and it's pointing in the direction that the force is being exerted, right?
Yeah. Yeah. Now,
So I was wondering, for the green pair, it's the earth is acting on the frog and the frog is acting back down the earth.
yeah.
But for the table, I see the arrow has its tail planted on itself, going downward when it's the frog that's pushing down on it.
Oh no. Well, there's 2 things pushing down on the table. See, that's the frog is pushing on the table. That's true. This is this red one.
The frog. Okay. But shouldn't that be on the frog because the frog's exerting the force? I was sort of comparing that to the green arrow on the earth. It's like, because that arrow is showing that the earth is exerting the force upward, but the red arrow on the table is on the table pointing downward.
Okay, so let me go back to the green one. I don't know if you meant to say this, but let's just start one at a time. The earth is pulling down on the frog. Fair enough. So I got the green arrow going down.
Yeah, I think so.
Right. So like a rock, if you just let a rock go, forget the table for a moment, what would happen to the frog? It'd be pulled down towards the earth.
I guess it was just a question or confusion about how you illustrated it.
Yeah. So I'm going to put a green arrow down because the earth is pulling down on the frog.
Yeah.
So
and
on
for the other one, the earth is exerting the force upward.
No, okay, careful with your words. The earth is not exerting the force upward.
Oh, sorry.
The frog is exerting an upward force on the earth.
Right. Okay.
Okay, so let me just go back to Newton's third law, right? If the earth puts a force on the frog down, then the frog puts a force on the earth up.
Okay. I get it. Yeah.
Yeah. So this force right here is from the frog. That's why there's an F here. And it's on the earth. And it's pointing up because it's upward.
I think I got that fixed
Okay.
up. Yeah.
Yeah. So then the same thing in this red one is the table is pushing up on the frog. So the frog is pushing down on the table. Mm-hmm.
I might come back and try to find the apple example because I thought there was a bit of contradiction. So
Sure.
yeah.
Oh, looks like the next page has an apple in it. No, that's a ball. It's a red ball. I thought it was an apple. Never mind. Yeah, I don't see anything here with an apple. But yes, I got to admit, this is we got to some real challenging parts now about what direction and how many forces are there.
Yeah, I'll keep looking in the last 5 minutes, I think.
Okay. Cool. All right. Let me jump back to the chat here. That's not it. And I saw Johnny come in. Did he send me a question? No, I guess not. All right. Maybe he's working on it. I don't see him now. Okay. All right. So,
I feel like this is where we have to kind of hone in on the definition of a companion force. Like,
yeah.
because-
Yeah. Right. Okay. So let me get my screen going here. So it says, okay, so it says a branch exerts an upward force on an apple in a tree. All right. So let me just roughly draw a tree. Got this branch sticking out. And somewhere here is an apple. All right. Now, don't forget there's an earth. And so kind of like the problem we just did, there is three objects we should be talking about here. One is the earth, another is the tree, and another is the apple. Okay.
Mhm.
All right. So the branch is lifting up on it.
Yeah.
And so actually maybe I'll kind of try to do the same color coding that I did back here. I talked about the earth pulling down on the frog, and I did it in green. So I'm going to do the same thing. The earth pulls down on the apple. That's called its weight. So I would put force, and it is from the earth, and it is on the apple. According to Newton's third law, then, there would be a force from the apple on the earth, and it would be pulling the earth up. So that's that same green pair.
I guess my first line of confusion was I thought they were talking about it's not the force of the apple pulling down from gravity.
Yeah,
they're talking about the lower green arrow.
Yeah. Okay. So no, wait. Okay. So let me just stay away from the question for a moment. Let me just draw two sets of forces. I won't draw it as complicated as before. I'll just draw the two on the apple, okay, which would be like this frog. So I'll draw the green one and the red one, okay? So I've drawn the green one. Now let's talk about the red one. See, the apple is in contact with the tree. So the tree is lifting up on the apple. So there'd be a force from the tree on the apple. And since the tree is lifting up on the apple is then pulling down on the tree. So there would be a force from the apple on the tree. So these two red ones are the third law. They're on different objects. One is on the apple pulling it up, the other is on the tree pulling it down. And the green one is Newton's third law. It is pulling down on the apple and up on the earth. These two right here are each on the apple. And there would be forces between the tree and the earth, but that's where it gets kind of complicated. And I don't think we need to include all that. I was including it here to try to help you, but I'm going to stay away from it on the second one and say, okay, now let me come to the question. The question says, a branch exerts an upward force on the apple in the tree. Now one plot right there. They're talking about this red one. Right? This red one is the upward force on the apple from the tree. That's what that's meant. From the tree on the apple. That's the first sentence.
Right.
And then it says, what is the third law companion to this force? And so in other words, what is it equal and opposite? And that would be this red one right here. It would be a downward force from the apple on the tree. That one. And I'll read the answer.
Okay, so it's the apple pulling, right?
And so it, got to make it a little bigger so I can read it better. It says, here's the answer, how they describe it. It says, it is the downward force, so there it is, downward force, of the apple on the branch. Note that this is not the downward force of gravity on the apple. See, that's that one. The downward force of gravity on the apple is this one. This green one is on the apple. This is on the branch.
Okay. Right. So it's kind of like, so so the earth is, so the apple is being pulled by the gravity, but then that in turn is pulling the branch. I guess. Oh no, the like the gravity of the apple from the apple is pulling the branch, I suppose.
Well, I don't want to say there's not a cause and effect, but those are not the third law. The third law is the green ones is the third law here, and the red ones are the third.
Okay.
And I think what you're expanding on is saying then that if you look at the second law here, where you add up all the forces on the apple, which has to equal the mass of the apple times the acceleration of the apple. Normally, the apple is not moving, it's not falling, it's just hanging there. So we could say this has to be zero because the acceleration is zero. And that would tell me that these two forces right here, the green one and the red one, are equal.
Right. Okay.
And notice I said they were equal because of Newton's second law, not the third law. The two red ones are equal because of the third law. The two green ones are equal because of the third law. But why am I saying the red and the green one are equal is because there's zero acceleration, which is the second law.
Okay. Well, I have a lot to think over.
Okay. Yeah, and you touch on something well. It takes a lot of thought to distinguish between these, and so don't feel like you got to get it in one shot or one day or even in one chapter here. These come together over a series of the next couple of chapters.
Right. True.
But it sounds like you're doing the right thing by struggling with it and fighting with it and saying, okay, which one is which?
Yeah, I guess I got a little bit confused from the beginning about like what was exerting what from the answer of that one problem.
Mm-hmm. So I think the author says this really well and carefully when he says in the answer on the second sentence, he says, note that it is not the downward force of gravity on the apple. So he's trying to make it clear that this green one is not the same as this red one. The green one comes from the earth. The red one comes from the tree. Now, they are hooked together because of the fact that the apple is then tied to the branch, the acceleration is zero, and we can conclude then that this force down on the branch, which is red, which is the same as this red one because of the third law, and because of the second law, this red one is the same as the green one, There it is. We could say that the downward force on the branch is the same magnitude as the force of gravity from the apple, but it's not the same force. It was a chain of events. In fact, maybe that's a good way to describe
Okay, I see. The chain of events. Okay.
Yeah, if I took a chain and I pull on this link, I'm actually pulling on this link. And you would say, well, but that link is tied to a cart. And so does my force pull on the cart? Well, no. Your force pulls on this chain, which then pulls on the next link and the next link and the next link and the next link. It's this link that pulls on the cart. It's not your hand, but obviously there's a chain of events that result. And you wouldn't have the cart being pulled on if your hand wasn't pulled. And just like this, if we didn't have the force of gravity, we wouldn't have this upward reaction force, which we wouldn't have this downward reaction force. So, there is a chain of events. They are connected, but they are different forces.
Okay. I think that makes sense.
Oh, good.
Cool. All right. Thank you.
All right. Take care.